Negativity is never desired. Its effects can be drastic, but matrices seem to be happy with this phenomenon. You are watching the types of matrices, and we are talking about the negative of a matrix. This one is quite simple. Take a matrix A and just change the signs of all the entries from positive to negative and negative to positive. 1 becomes -1, -2 becomes 2, then -3 and -4. What you got is the negative of matrix A, and it is denoted as -A. Now for the next type. Do you know what symmetry means? It means similar or look alike. For a matrix to be symmetric, it should be equal to its transpose, meaning matrix A is symmetric if the transpose of A is equal to A. But when can we be sure that A and the transpose of A are equal? What actually is equality? Recall that two matrices are equal if they satisfy the following conditions. Number 1, the orders should be the same. Number 2, their corresponding entries should be equal. This means that any rectangular matrix such as these two is not in this race, as its order changes once you take its transpose. That's what we learned in a previous lesson, right? So, this only leaves us with the square matrices because their order remains the same after the transpose. That fills the first condition of equality. But is every square matrix always symmetric? No. Here you apply the second check. If all the corresponding entries of the original matrix are the same as of the transposed matrix, then it is symmetric. Let's look at this through an example. Take a square matrix M of order 3 by 3. It may be symmetric because its transpose will have the same order as M. To confirm, check the second condition. Find the transpose of M by interchanging the rows and columns. Are all the corresponding entries the same? Yes. So is the transpose of M equal to M? Definitely. Since both the conditions of equality are fulfilled between M and the transpose of M, therefore matrix M is a symmetric matrix. Let's look at another example. Take a matrix A. Find its transpose. Is it equal to A? Well, the orders of the two matrices match, but the corresponding entries such as 1 and -1 up top and the circled 2 and 1 do not match. So A is not symmetric, even though it is a square matrix. There is another kind of symmetric matrix called the skew-symmetric. This type is valid if this A transpose equals -A condition you see on your screen holds true. Basically, it's the same as a symmetric matrix, but instead of A, we have the negative of A here. Let's look at it through an example. You need to find two different things from matrix A. First, find the negative of A by reversing the signs of each entry. 0 has no sign, so we do nothing. 2 becomes -2 and 3 becomes -3 and so on. Next, find the transpose. That is done by interchanging the rows and columns. There you have it too. Now, let's see if these two are equal. The first thing is the order, which is the same because matrix A was a square matrix. Secondly, the corresponding values 0 is equal to 0, -2 is equal to -2, -3 is equal to -3, and the rest are the same as well. So, in this case, both matrices are equal A transpose equals minus A. Therefore, A is a skew-symmetric matrix. I hope you are clear on these topics now. We will cover some more topics in the next lesson.